So in this video, I want to go through and finish up the back side of homework 15A. So we pretty much did the whole front side and most of the back side, but then there's just this little section on the bottom that says Dalton's law of partial pressures, starting with number 17. So that's the one we're going to do. I guess technically this has a little bit of notes in it because there is a paragraph in the notes. This is notes 15. And there's just this little blurb on Dalton's law of partial pressures. This is the same John Dalton who came up with the solid sphere model back in Honors Chem. And basically what he said is that the total pressure exerted by a mixture of gases in a container is the sum of the pressures that each would exert if it were alone. So what that means over here, you have two containers. In one of the containers, we have a certain number of gas particles and they're exerting pressure on their container. And for simplicity, let's just say that these particles are exhibiting 3 pressure, and these ones are exhibiting 4 pressure. So if I put them together in a tank that was combined, these would be contributing to what, like 3/7, and this would be 4/7. 3/7 and 4/7. This is exerting slightly more pressure because there's more fraction. Like this is the bigger fraction when they come together. That's all partial pressures is. It's just saying, first off, that pressure is the force being divided over the area. Okay, you already know that. And when you have a mixture of gases, the sum is equal to what it would exert if it were alone. It is the total number of moles that's important, not the identity of the gas. And here are some fancy equations for this thing called a mole fraction. And I know you're thinking, oh, a mole fraction, a mole fraction. It's probably just where you make a fraction of how many moles there are, right? And I would say that's really good logic, just like I did over here. 3 out of 7, 4 out of 7, 1, 2, 3, 1, 2, 3, 4. But actually, mole fraction is that, but it's in decimal form. I don't know why they don't call it mole decimal, but it really should be mole decimal. So mole, air quotes, fraction is like a fraction, except for it's a decimal. Ugh, really annoying. But we'll do some homework examples and you'll kind of see how this works. So there's the end of the Dalton's law of partial pressures in the notes. And here are some examples where we go through Dalton's law of partial pressures for the homework. So let's start off simple with number 18. The partial pressure of oxygen was observed to be 156 torr in air with a total atmospheric pressure of 743 torr. Calculate the mole fraction of the O2 present. The air that you breathe in, take a breath. Okay, whatever. Oh, my dog's like, what are you doing? What am I doing? Come say hi. Come here. Come here, girl. Come say hi. Up, up, up. Oh, hello. Oh, you're stuck. Here we go. Did you know that the air that we breathe, most of it, like 80% of it, is nitrogen? Oh, bye. So like 80% is nitrogen and only like 20% is oxygen, just in what we normally have. So what this is saying is that the normal pressure that's being exerted on this particular spot in the world is 743. The oxygen is putting this much pressure. That's how much oxygen is contributing. And this is the total pressure. It wants the partial pressure, or sorry, it wants you to calculate the mole fraction, aka mole decimal, of the O2 present. So on the front, there's this equation that says mole fraction, and here's the symbol for mole fraction. You can look in the notes. Mole fraction, it's like a fancy letter X. Equals the number of moles of what you're looking at, number of moles of the number of moles of O2 divided by the number total. Or you can also think of this as the pressure of the oxygen over the pressure total. It's just a fancy way for you to literally go, great, the oxygen is contributing 156 of the torr out of the 743 torr. I would say this is a fraction, but mole fractions are actually mole decimals. So 156 divided by 743 is 0.209. This is the mole fraction, even though it's a decimal. Of the amount of O2 that's in the air, which is basically what I said. I said that when you take in a breath, you get about 21% oxygen, and the rest, what would it be, 80 or 79% or whatever, would be nitrogen, but this was irrelevant for the problem. So that's mole fraction. It's pretty easy. You can do the same math, but backwards, where it gives you the mole fraction. It says the mole fraction of nitrogen in the air is this. So, which is about what I just said. I said 79 and it says 78%. That's okay. So nitrogen is 0.78. What is the partial pressure of N2 when the total atmospheric pressure is 760? That would be at sea level, because 760 torr is 1 atmosphere. So we're basically asking, what is 78% of 760 torr? And if you wanted, you could convert into atmospheres and say 593 torr out of 760 torr. This is how many torr is in an atmosphere. So we have this many atmospheres. But the problem just wanted you to find the partial pressure. So mole fractions are really, really simple. It's basically just calculating a percent. This next part here, number 20, we've got 3 different gases that are being shoved into a container. We have 1 liter, let's see, 1 liter of oxygen at, it would be 2 atmospheres of pressure. Let's see, 2 liters of nitrogen at 1 atmosphere of pressure. Daisy, you okay? You're breathing hard over there. Why don't you just roll over and then you'll be more comfy? Sorry, I had to roll my dog over. She was just like breathing funny. Anyway, so we've got these 3 mixing together, and they're getting mixed into a 3-liter vessel. So they're getting like pushed in, compressed, and we're wondering what's the final pressure of the mixture in this container. So let's first figure out if we can figure out the pressure of what the oxygen would be shoved into the container alone, and the nitrogen shoved into the container alone, and the helium shoved into the container alone, and then add them up, that would be the sum. So what we can do here is similar to what we did in the other assignments. We're looking at the relationship between pressure and volume. The pressure will change as we squish it, into a different container. So let's say we got PV equals nRT, and we're actually already set up perfectly because we've got pressure and volume on the same side. So PV equals nRT equals PV. Get rid of the middle. PV equals PV. And I'm going to plug in some of the values that I know. I know that on one side, we're going to have 2 atmospheres and 1 liter, and the volume will then change to 3. That makes sense? So I'm going to rewrite this as, let's see, P1 V1 equals P2 V2, where V2 is going to be this 3 liters. So let me rewrite this. I've got P1 V1 over P2, or sorry, I meant to write V2 down there, over V2 equals P2. This is the pressure of the oxygen on its own. This will be the pressure of just the oxygen in this new container. So it started out with 2 atmospheres and 1 liter. And I can keep it this way if we'd like, that's fine. P1 V1 equals pressure of the oxygen, and the new container is 3 liters. Solve for the partial pressure of the oxygen. 2 times 1 divided by 3 equals partial pressure of the oxygen is 0.66 repeating atmospheres. That's how much the oxygen is contributing once we put it all together. I'm going to do the same thing for the nitrogen and the helium. For the nitrogen, I have let's see, did that wrong already. For the nitrogen, I have 1 atmosphere of pressure. The original volume is 2 liters. I'm trying to find the partial pressure of the nitrogen when the container changes to 3 liters. But I'm going to put 3 liters in black because it's like the combined container. One times 2 divided by 3. Same exact thing. The pressure of this one is 0.67 atmospheres. This is how much the N2 is contributing. This is how much the O2 is contributing to the pressure. Last but not least is the helium. We have 2 atmospheres and 2 liters of it. We're trying to find the pressure of the helium when the volume changes. This is getting squishy, to 3 liters. 2 times 2 divided by 3 is 1.33. The partial pressure of the helium is 1.33 atmospheres. So if the helium is pushing 1.33 in this new container, the nitrogen is pushing 0.67 in this new container, and the oxygen is pushing 0.66 in the new container. What is the final pressure in the container? 0.67 plus 0.67 plus 1.33 equals 2.67. If you wanted, you could figure out the mole fractions. You could do the 0.66 divided by 2.67, get the mole fraction of oxygen, mole fraction of nitrogen, and take 1.33 divided by 2.67. That would be the mole fraction for helium. So this is a really good example of just what the notes is saying when it says that the total pressure exerted by a mixture, aka 2.67 here, is the sum of the pressures that each would exert if they were alone. Okay, number 17 is a little bit more tricky. Mixtures of helium and oxygen are used in scuba diving tanks. For a particular dive, 46 liters of helium at 25 degrees Celsius and 1 atmosphere, that is mixed with 12 liters of oxygen, same conditions, essentially 46 liters of helium, 12 liters of O2 are pumped into a tank, and the tank has a volume of 5 liters when it's combined together. We need to calculate the partial pressure of each gas and the total pressure in the tank. So see how it's kind of a similar problem. Down here we had 3 gases getting mixed together into a 3-liter vessel. Here we have 2 gases being combined into a 5-liter container. Now it's going to be very compact because it's normally, under these conditions, this much. And we're going to really pack it in there. So this one does take a little bit of space, or at least like when I did it, it took a little bit of space. You guys are definitely smarter than me, but I'm going to do it on some extra paper so I don't have to worry about running out of space. If you do it on your calculator, though, you won't run out. So we need to calculate the partial pressure and the total pressure. What I think would be useful is I'm going to divide this into like a part A, part B type situation. And for part A, I'm going to do the mole fraction of these two gases. Basically, I'm just trying to see how many moles of helium there are and how many moles of oxygen there are. So to figure out the moles of helium, let's see, I'll divide it like, I don't know how I'm going to divide it. Maybe I'll just color code it. I'm going to do helium in this like orangey color. Helium PV equals nRT. The pressure, it said it was at 1 atmosphere. The volume was 46 liters. PV equals, I don't know the number of moles. I'm trying to figure that out. R is always 0.08206. And the temperature is 25 degrees Celsius, which adding 273 is 298 Kelvin. So this is how I'm going to get the moles of helium. And for this, I just punched in really quickly. I'm getting 1.88 for my number of moles. I'm just going to round that. So number of moles of, is this the helium? Number of moles of helium is 1.9. Next thing, same process, but I'm going to do it for the oxygen here in green. PV equals nRT. Pressure, temperature, I need to convert it. Volume, let's see, 1 atmosphere. The volume is 12 liters. Don't know the number of moles. 0.08206 as always, and the temperature I already converted, 298 Kelvin is 25 degrees Celsius. And for this one, I'm getting 0.49. So the number of moles of, is this oxygen? Yep. The number of moles of oxygen is 0.49 moles. So I have this many moles of oxygen going in to the tank. I have this many moles of helium going into the tank. I have way more helium in this tank than I do oxygen. Now what it wants me to do is calculate the partial pressure of each gas. Let's see how much this is contributing to pressure, how much this is contributing to the total pressure, and then add them together, and then we'll know the total pressure. So what I'm going to do is scoot down my paper here. We don't need anything other than the final answers that we got from above for this. So for the helium calculation, we already know that we have this many moles. PV equals nRT. That's going in for N. The volume is changing though, because this is the volume of like the combined container. The problem says that the combined container is 5 liters. The temperature for the combined thing will stay at 25 like it always has been. So that's going to stay at 298 Kelvin. And R is always 0.08206 for these calculations. So I'm trying to see what pressure is this amount of helium putting on the new tank. So let's see. P times 5 equals 1.9 times 0.08206 times 298. Solving for P, pressure equals, calculator. I'm getting 9.29. I'm going to round that to 9.3. The helium inside this new container is exerting 9.3 atmospheres. This is how much pressure, I'm going to put HE, the helium is exerting in the new combo container. Wow, that's blurry. My apologies. Same thing. Let's figure out how much pressure this oxygen is exerting in the new tank. The temperature didn't change at all for this problem. It was just 298 Kelvin the whole time. R, hopefully you have that memorized by now. The number of moles of oxygen we'll get from there. The volume of this total tank is 5 liters from the problem, and we're solving for the new pressure of oxygen. P times 5 equals 0.49 times 0.08206 times 298. The pressure of the oxygen equals 49 times 0.08206 times 298 divided by 5. I'm getting 2.396. I'm going to round that to 2.4. The oxygen is pressurized up to 2.4 atmospheres in our new combo tank. The question asked us to calculate the partial pressures of each. We did that, 9.3, 2.4, and the total pressure in the tank. Total pressure in the tank would be 9.3 plus 2.4. There you go. So that's how you do all of the problems. I think we did all of them. All of the problems on Dalton's law of partial pressures. It's basically use perv-nert separately, solve for your moles, then use the mole fractions when you have it combined into a tank together. Your mixed pressures will add up to the total.